Hello, I am Palid Maheshwari from Department of Chemistry, Government First Grade College, Bidar. Today I'll be dealing with the continuation of adsorption, that is adsorption with dissociation, and what is competitive adsorption. Adsorption with dissociation. When we come to this concept, it is the process of adsorption is accompanied by the dissociation of a molecule on the surface. For example, hydrogen is adsorbed on the surface of many metals in the form of atoms, each of which occupies a surface site. Similarly, methane adsorbed on metals usually is dissociated into methyl, ethyl, and hydrogen atoms. For example, if you are going to see the figure wherein I can consider an atom, a molecule A2 is going to be adsorbed on the surface which is mentioned as S, and here the molecule is getting dissociated and getting adsorbed on the surface as atoms. That is, the process of adsorption is then a reaction between the gas molecule and the two surface sites, and the rate of adsorption therefore may be written as, that is, rate of adsorption is written as Ra is equal to Ka into concentration of A into 1 minus theta square. Actually, theta refers the number of molecules which are the number of atoms which are going to be adsorbed on the surface, and 1 minus theta involves the surface available for adsorption. The desorption process involves the reaction between the two adsorbed atoms, and the rate therefore is proportional to the square of the fraction of the covered surface. That is, rate of desorption will be R minus A is equal to K minus E theta square. So at equilibrium, the rates becomes equal, and on rearrangement of the expression, we get theta by 1 minus theta is equal to K by K minus A into the concentration of A whole to the power of 1 by 2. And K is going to be the equilibrium constant, and it is the ratio of Ka by K minus A. The equation can now be written where the fraction of the molecules which are going to be adsorbed after the dissociation into atoms is written as K to the power of 1 by 2 concentration of A to the power of 1 by 2 divided by 1 plus K A to the power of 1 by 2 by A to the power of 1 by 2. When a plot of theta versus the square root of A is plotted, which is going to be shown in the next slide, when the concentration is very small, that is K to the power of 1 by 2 into A to the power of 1 by 2 is much smaller than unity, and theta is proportional to A to the power of 1 by 2, the equation may be written as 1 minus theta is equal to 1 by 1 plus K to the power of 1 by 2 into A to the power of 1 by 2. At higher concentration, when K to the power of 1 by 2 into concentration of A to the power of 1 by 2 is much greater than 1, then the equation will be written as 1 minus theta, which is approximately equal to 1 by K to the power of 1 by 2 into A to the power of 1 by 2. So this is the fraction of the surface, that is, where at higher concentration is therefore inversely proportional to the square root of the concentration or pressure. So the graph represents like the equation which is mentioned. That is, when the surface is barely covered, the equation theta is equal to, if it is going, it will be equal to K to the power of 1 by 2 into A to the power of 1 by 2. If it is going to be well covered, then the surface will be 1 minus theta is equal to 1 by K to the power of 1 by 2 into A to the power of 1 by 2. So this graph is going to represent it. Next, coming to competitive adsorption. Now, actually, what does this competitive adsorption mean? This means when two species A and B that are going to compete for the same adsorption site is known as competitive adsorption. The kinetics of surface reactions involving two reactants can be mentioned. That is, if I am having theta A is going to be the fraction of the molecules covered by the molecule A, and the fraction covered by molecules B is written as theta B. The fraction which is available for adsorption is going to be given as 1 minus theta A minus theta B. If both the substances are adsorbed without dissociation, then the rate of adsorption of A and B are given as rate A to the power of A will be equal to Ka into concentration of A into the surface available for adsorption. Likewise, the rate of adsorption of B will be given as Ka to the power of B into concentration of B and the surface available for the adsorption. The rate of desorption will be represented as, that is, rate of minus A will be equal to K minus A theta A. That is, already the molecules which are adsorbed, they are only available for desorption. Similar is the case with the rate of desorption of molecules of B. Now these expressions, when we are going to equate, that is when rate of adsorption will be equal to rate of desorption, the expression for will be given as theta A by 1 minus theta A minus theta B will be equal to Ka into concentration of A. Likewise, for theta B, the expression is going to be written as theta B divided by 1 minus theta A minus theta B, and that is equal to Kb into the concentration of B. Now these expressions gives us the fraction of the molecules during competitive adsorption, the fraction of the molecules adsorbed by A and the molecules B. Theta A will be given as K into concentration of A, which are going to be adsorbed, by 1 plus Ka into concentration of A plus Kb into concentration of B. Theta B is going to be Kb into concentration of A by 1 plus Ka into concentration of A plus Kb into concentration of B. So this is the case because the molecules of A and B are competing with one another for the limited number of sites as we speak for competitive adsorption. Thank you.